Okay, geometry fans, this is going to be day 5 of circles, and our topic today is chords and tangents. We're actually going to break this into 2 lessons. We're going to use basically the front side of the notes will be today's lesson. We'll talk about chords and relationships with that. And then tomorrow we'll talk about measures with tangents, which will be the back. Okay, so to start off here, your geometry joke of the day. What do you call a teapot of boiling water on top of Mount Everest? What do you call a teapot of boiling water on top of Mount Everest? And the answer is a hypotenuse. High pot in use. There you go. Okay, so let's take a look at this here. And you're gonna need to have a compass today because we're gonna construct some circles, and we want to be as accurate as possible for this. Now, for number 1, there are basically 3 ideas with chords that we're going to talk about, 3 relationships. The first one here, and we have a theorem, and it says in a circle or in congruent circles, 2 minor arcs are congruent. IFF, their corresponding chords are congruent. IFF, if you see that, that's a shorthand for if and only if. So in a circle or incongruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. Basically what that tells us is that the statement's going to work both ways. The conditional and the converse are going to be true. And I'll explain this with the picture. So in this picture you have an inscribed triangle, okay, where the points A, B, and C are on the circle, but the sides are inside the circle. Notice it also, all 3 sides are congruent. So that's an equilateral triangle. And what happens here, what this theorem is saying is that these chords, these are all chords because both endpoints are on the circle. If the chords are congruent, then the arcs also have to be congruent. If the chords are congruent, then the arcs that get created by the chords also have to be congruent. Okay, so the way that we're going to write this here, beneath the picture, we'll say if segment AB is congruent to segment BC is congruent to segment AC. If that's true, then we know that arc AB has to be congruent to arc BC, which has to be congruent to arc AC. So what the theorem says is that if the chords are congruent, then the corresponding arcs are congruent. And since it's if and only if, it also works the other way, where we can say if the arcs are congruent, then the chords that get created have to also be congruent. So that's what the theorem is saying. And as an example here, if you think about this, you know in an equilateral triangle, all the angles are 60. So angle C has to be 60 degrees. Now, if I trace that out, that's an inscribed angle. That's going to hit the circle at point A. It's going to hit the circle at point B. And so that intercepts arc AB. Now this vertex is on the circle. So on the circle is half the arc. So if this is 60, this has to be 120 degrees. Now if angle A is also 60 degrees, and it is, because it's equilateral, then you know that this is also 120. And then you know that this is also 120. Okay, so that's demonstrating this relationship. So let's look at the examples, number 1 and number 2. Find x and find y. Well, there are a couple ways to do this, but the easiest way is going to be, let's count the sides here. This is a hexagon, 1, 2, 3, 4, 5, 6. 6 sides, they're all congruent. All the chords are congruent. That means that all of these arcs have to be congruent. Now you know that arc measure always adds up to 360. Well, how many of the arcs do we have? 1, 2, 3, 4, 5, 6. So divide by 6 and you get 60 degrees. So the value for y is going to be 60. Now to get x, x is not an arc measure, x is an angle. And the vertex of the angle is on the circle right here. If we trace out this angle that creates x, it would intersect the circle here and here. And so this would be your arc that gets intercepted. Now, let's see, we can figure out what that arc measure is because you have 1, 2, 3, 4 of these arcs. All of these are 60s. So 4 times 60, this whole thing here has to be 240 degrees. Now, if it's a central angle, it's the same. If it's on the circle, it's 1/2. So it's half of 240. The angle measures half of 240. So 240 divided by 2 is 120 degrees, and that's equal to x. That's your answer. Okay, let's look at number 2. Now number 2, think about what kind of quadrilateral would this be. All 4 sides are congruent. So it's either a rhombus or a square, but it kind of looks like a square, doesn't it? And now let's see, that means we have 4 arc measures. 1, 2, 3, 4. They're all congruent because all 4 sides are congruent. So all the arc measures always add up to 360. There's 4 of them, so we divide by 4. So each one is equal to 90. So the value of y is 90. So we get that right away. All right, now look at x. X again is inscribed. The vertex is on the circle. Now where do the angles hit the circle? Here, where the sides hit the circle, and here. So it creates this arc. Now this is actually 2 of these 90-degree arc measures. That's 90 and that's 90. So that's a total of 180 degrees. Well, if it's on the circle, it's half. So half of 180, 180 divided by 2 is equal to 90. So in this case, y is equal to 90 and x is also equal to 90. And that's it. Okay, so that's our first relationship. If the chords are congruent, the arcs are congruent. If the arcs are congruent, then the chords are congruent. It works both ways. All right, theorem number 2. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. Now this is where we're going to be using the compass. All right, so let's go ahead and put a point here for the center. We're going to make this as accurate as we can. Now, the circle does not need to be huge. It doesn't need to be big. Okay, so I'm going to make the setting pretty small. Let's see if I can get all the way around here. Okay, that looks pretty good. There's my circle. Now we have a center. Now what we're going to do here, let's draw a chord. So a chord is just a segment in a circle where both of the endpoints are on the circle. So let's call that chord AB. And then let's call this point here, the center, C. So this is the circle with the center at C. Now, what we want to do, it says in the theorem, if a diameter is perpendicular to a chord. Well, let's see, so how are we going to do that? If a diameter is perpendicular to a chord, we want to draw a diameter, so through point C, that is perpendicular to AB. Well, to do that, this is like a point, and we're trying to draw a perpendicular through this point to this line, and so we're going to anchor on C. I'm going to make the setting very small here because what I want to do is I'm going to arc through both sides. Oh, let's see, that didn't work so well. Let me try that again, where this is not moving. There's the first. Okay, there's the second, so that looks a little bit better. And what we'll do here, I'm going to open this up, and then I'm going to arc above and below from both of these points. Okay, let me turn this here. Anchor on that point. I'm going to arc above and below. This is also good practice of our constructions here. And then we're going to connect this. And if you've done this right, it should go through point C, and it should also look perpendicular. It should look perpendicular to AB, and it should also go through point C. Now, mine actually looks like it's a little bit off, maybe not quite 90 degrees. It's close, but that's okay. Now, here's what we're talking about. Here's our diameter right here. It's perpendicular to the chord. One thing you want to think about anytime that you have perpendicular, anytime you have a 90-degree angle, the question is, can we get a right triangle? And the answer to that is yes. If we connect point C and point B, we just created a right triangle. And actually CB, well, if you think about that, what kind of segment is that? It is a radius. And I'm going to call that R. Now, if I did the same thing with C and A, that's also R. If you look at these two triangles here, you know that the radii are both congruent. You know that this segment right here, let's call this point D, CD, by the reflexive property, is also congruent to itself. So we've got the hypotenuses are congruent, and we've got this leg here is congruent. So are the triangles congruent? Yes. The triangles, we can say triangles congruent by hypotenuse leg. Triangles congruent by hypotenuse leg. And if that's true, then that means that AD and DB have to be congruent, those two segments, by CPCDC. If the triangles are congruent, then the corresponding parts of congruent triangles are also congruent. So what the theorem says is that what we just proved, if the diameter is perpendicular to a chord, it bisects the chord. It bisects. So these two segments have to be congruent. That's always true. So AD is congruent to DB. And the other thing that happens here, anytime you have a right triangle, don't forget about Pythagorean theorem. Okay, don't forget a squared plus b squared equals c squared. Anytime you have a right triangle, we're thinking Pythagorean theorem to solve, to find values. Okay, now I'm going to stop here for a second, and then we'll look at this example.